So let us start today's session. I am Dr. VC Solteke. So objectives of today's video lecture are first to define and explain Newtonian heating or cooling, and second objective is to explain lumped parameter analysis method or lumped capacity analysis. Let us start our discussion with Newtonian heating or cooling, followed by the explanation of lumped parameter analysis or lumped heat capacity analysis. So Newtonian heating and cooling, and this Newtonian heating and cooling is analyzed by lumped parameter analysis method or lumped capacity method. So lumped parameter analysis or lumped capacitance method is used to study transient heat conduction phenomena when thermal conductivity of the object, which is in transient state or unsteady state, is infinite. This is the prerequisite condition to apply actually lumped parameter analysis. Now, what is this method is all about? So let us discuss about this method. Now, in order to understand Newtonian heating and cooling, first let us consider case 1, where heating or cooling of a body takes place having its thermal conductivity value finite. That means it is having a finite thermal conductivity value. Now, in actual practice, what happens, or many times what happens, thermal conductivity of almost all the objects are having finite value. And when such object is undergoing heating or cooling by virtue of heat transfer into or from that system, its material, that is material of the body, offers a thermal resistance as we have studied in unit 1, and by virtue of that there exists temperature gradient within the body itself. That is, its different surfaces will be maintained at different temperatures. Okay. To understand what I'm trying to say, consider this body in which some heat transfer rate is taking place, because of which either it may undergo heating or cooling. It is having a finite thermal conductivity value K, and its thickness is capital L. Let's say the rate of heat transfer is Q. Now I know, and the body is exposed to the fluid at temperature T infinity and convective heat transfer coefficient H on both sides. Let's say same fluid is covering this body on the same side. So we know the internal conductance resistance of this body will be L over Ka, and surface convective resistance by the fluid will be 1 over Ha. That is, when heat transfer is taking place across this phase and this phase of this body with with finite thermal conductivity K, the material of the body will offer this much thermal resistance to the heat transfer, and surrounding fluid will offer this much convective resistance to the heat transfer. In this case, I am also considering the surface area and volume of this body are comparable. Now, as a result of some finite thermal conductivity value, the body is going to offer L over Ka internal conductance resistance, and the surrounding fluid is going to offer 1 over Ha convective thermal resistance. And because of this resistance offered by the body of the material, the surface, left surface and right surface of this body will have different temperature. Let's say at T1 and T2 respectively. That means because of finite thermal conductivity value of the body of the material of the body is going to offer some internal conductance resistance that will create temperature gradient across the surfaces of this body. Okay. Now let us consider case number 2. Heating and cooling up a body with infinite K value. In this case, I am assuming the thermal conductivity of this body is tending to infinite value. So let us consider again one such body in which heat transfer rate is taking place, having thermal conductivity value, and its value tends to infinity. Its thickness in the path of the heat flow is L, and here I am assuming surface area of the body is very large as compared to its volume. Now under such conditions, what happens when the body is having infinite thermal conductivity value and its surface area is very large compared to its volume? In this case, what happens? The internal conductance resistance, now which is L over Ka. Now K is infinity, almost infinity, and this surface area is very large compared to its volume. So internal conductance resistance almost becomes equal to 0. And surface convective resistance will be 1 over Ha. If it is exposed to the fluid at temperature T infinity and convective heat transfer coefficient on both the sides. Now, what is the difference then? What is the difference between case 1 and case 2? In case 1, I have assumed finite thermal conductivity value, and because of that, the material is going to offer some internal conductance resistance L over Ka, and that finite internal conductance resistance value is going to create temperature gradient across the surface of the material. While in second case, thermal conductivity value is tending to infinity and surface area of the body is very large compared to its volume. And as a result of this, internal conductance resistance of the material is almost zero, whereas convective resistance is offered by the surrounding fluid. Now, this internal conductance resistance is basically responsible to create temperature gradient within the surface of this body. So, if it is zero at all, there will be no temperature gradient across the surface of this body. Temperature at these two surfaces of the body will be equal to zero. So let me conclude this. When a body is having infinite thermal conductivity and its surface area is very large compared to its volume, and if such body is undergoing heating or cooling, in this case, internal conductance resistance offered by the body of the material is zero, and as a result of this, no temperature gradient exists across the faces of the body, or there is no temperature gradient at all within the body itself. The entire body surface is assumed to be maintained at the same temperature everywhere, and under such condition, the entire heating or cooling process is governed by the surface convective resistance of the surrounding fluid. And if such body is undergoing heating or cooling, this process is called as Newtonian heating or Newtonian. And if Newtonian heating or Newtonian cooling is taking place, to find out the temperature of the body under such condition, I can apply lumped parameter analysis or lumped capacitance method to find out the variation of the temperature of this body, which will be function of time. So this is basically, you can say, foundation theory behind the lumped parameter analysis and its application. So when a body is heated or cooled and its internal thermal conductance resistance L upon Ka is negligible because of K tends to infinity, but surface convection resistance offered by the fluid 1 upon Ha is very large. Such process is called as Newtonian heating or cooling. In Newtonian heating or cooling, the entire heat transfer process is controlled by surface convection resistance. And who offers this surface convection resistance? By surrounding fluid. In such case, no temperature gradient exists within the body, and all the surface temperature of the body, in our case T1, T2, at given instant of time remains constant and same. And because of uniformity of the temperature, body is considered as a lump. Now I will explain what is the meaning of this lump. Examples of Newtonian heating or cooling is heating or cooling of solid disks, thin solid disk, or thermocouple wire. Thermocouple wire you might have seen, they are of very small diameter. So when a thin metallic disc is heated or cooled, it is supposed to undergo Newtonian heating or cooling because surface area of solid thin disk is very large as compared to its volume. Similarly, surface area of thermocouple wire is very large as compared to its volume, and it qualifies for the Newtonian heating and cooling. And temperature of either this solid thin disk or thermocouple wire is assumed to be constant everywhere by virtue of zero or negligible thermal resistance. And under such condition, the entire process of heating or cooling is governed by the surface convection resistance of surrounding. So heating and cooling of thin disk and heating and cooling of thermocouple wire. These are the two examples of Newtonian heating and cooling. And since because of no internal thermal conductance resistance in case of Newtonian heating and cooling, temperature of the entire surface remains constant. The body is considered as lump. Now, what do you mean by lump? I am going to explain in subsequent slide. And the method of analysis is called as lumped parameter analysis or lumped capacitance analysis. So when I analyze the temperature variation of such body whose temperature is going to remain same and constant everywhere, that method is called as lumped parameter analysis or lumped capacitance analysis. Now, in order to understand what do you mean by lump actually, consider a copper ball with uniform temperature. So, this is a copper ball having its surface temperature 70 degrees Celsius everywhere. So, it can be treated as a lump. Another example, consider a potato taken from boiling water. Now, the moment you take out the potato from the boiling water, its temperature will be different everywhere. As you can see here, it is having different temperature at the different surface. Now, this potato cannot be considered as a lump as far as its surface temperature is concerned. So, the lumped parameter analysis cannot be applicable in this case. In case of copper ball with surface temperature 70 degrees Celsius, which is constant and same everywhere, it can be treated as a lump and lumped parameter analysis can be applied. Whereas in case of potato, just you have taken out from the boiling water, is having different surface temperatures at different points, we cannot treat it as a lump and hence lumped parameter analysis cannot be applied. To find out the variation of temperature as a function of time. Okay, what does it mean? Let's say at 9 a.m. the temperature of this body is 70 degrees Celsius. I want to know what will be its temperature at 12 p.m. It is definitely going to vary because it is in transient state. So that we can find out with the help of lumped parameter analysis. So now let us discuss what do you mean by lumped parameter analysis, how it is done. So in order to understand what do you mean by lumped parameter analysis, let us consider a hot metal forging as a solid body that is initially at a uniform temperature Ti and it is quenched by immersing into a liquid of lower temperature T infinity. Temperature of the fluid in which this hot metal forging is being quenched is T infinity is less than the temperature of hot metal forging. In a simple word, hot metal forging is immersed into a cold liquid. So this is a typical schematic of this cooling phenomena where this is nothing but body, and we have considered this body as a hot metal forging in this case. Initially it is at temperature Ti, so its temperature, what will be the boundary condition? At tau is equal to 0, that is initially temperature of this body is Ti. Ti is greater than T infinity. This is the liquid whose temperature is T infinity and convective heat transfer coefficient is H. Now let's say this hot metal forging is immersed into this liquid. So what is happening? Hot metal forging at temperature Ti is immersed into the liquid at temperature T infinity. There exists temperature difference between these two. So heat will start flowing out of this body, and that will be by convection method, obviously, because surface is exposed to the liquid. And temperature of this body will continuously vary, or in mathematical way I can say, once the body is dipped or immersed into this cold liquid, its temperature will be the function of time. So at any moment of time greater than 0, tau is greater than 0 means time after initial condition at any moment of time. Temperature of this forging or body will be function of time. So I want to find out what will be this T at a particular instant of time tau. So to understand the heat balance or heat equilibrium, let us consider this body as a control volume, and these surfaces are nothing but control surface. Control, the meaning of control volume, a body of fixed volume during thermodynamic steady is called as control volume, and the surface which surrounds the control volume is called as control surface. Now, how heat transfer balance is taking place into this body? So heat transfer is taking place out of this body by convection method, and because of this heat transfer taking place out of this body, its internal energy is decreasing. So rate of increase or decrease in internal energy of the body is equal to rate of heat transfer from the body by convection method. This energy balance we have to apply to calculate this temperature T, which is a function of time tau. So what is happening actually, the moment we immersed this hot body into the cold liquid during any differential time interval d tau, the temperature of the body decreases by a small amount d tau. If you consider time interval d tau, the change of temperature of the body will be d tau, dt, sorry. Since here cooling is taking place, so temperature will be decreased by a small amount dt. Now an energy balance of the body for the time interval dt can be expressed as heat transfer out of the body during time interval d tau by convection is equal to decrease in the internal energy of the body during d tau. and symbolically I can represent it by Q convection is equal to E out. That is rate of energy transfer from the body is equal to rate in the decrease in the internal energy of the body. Now from Newton's law of cooling, how can I calculate this rate of heat transfer? By this expression. H into As into T minus T infinity into d tau, that is time interval d tau, is equal to minus rho v Cp into dt. How did I calculate this E out? It is nothing but m Cp delta T. Mass is nothing but rho into density. So from that expression I could calculate change in the internal energy of this body. Since the internal energy of the body is decreasing, so I have provided negative sign. So this is the energy balance which is taking place at some moment of time. The body is being immersed into the cold liquid. Here this T is temperature of the body at any moment of time tau. Now let us rearrange this equation. Into this equation 1, rho is the density of the body in kg per meter cube. Capital V is volume of the body in meter cube. Cp is specific heat of the body, joule per kg Kelvin. Small h is convective heat transfer coefficient. As is surface area of the body in meter square, and T infinity is ambient temperature in Kelvin, and tau is time. And small t is temperature of the body at any moment of time in Kelvin. Now after arranging this equation number 1, it will give me dt over t minus t infinity is equal to minus HAS over rho v Cp theta. What I did, I just rearranged the terms. Now taking integration of this entire equation, integration of dt over t minus t infinity is equal to minus HAS over rho v Cp. All these entire properties are constant. H is a constant, AS is a constant, rho, V, Cp are constant. The only variable is time interval d tau. That is why I have taken integration of d tau. After doing its different integration, it will give me log of t minus t infinity is equal to minus HAS over rho V Cp into tau plus C1. Let's say this is equation number 2. Now, in this equation number 2, C1 is a constant of integration and I must know the value of this constant C1 because I am interested to calculate this T, that is temperature of the body after any moment of time tau. And unless otherwise I know the value of this constant C1, I cannot find out this value. So I must know the value of this constant C1. To find out the value of this constant C1, I must apply some boundary condition. So we have one boundary condition at tau is equal to 0, T is equal to Ti. What does it mean? Tau is equal to 0 means initially, before immersing the body into the cold media, its temperature was Ti. That means initially we were knowing the temperature of the body. So this is one such boundary condition. If I put this boundary condition into equation 2, it will give me log of Ti minus T infinity is equal to C1. Because in this equation, if you put here tau is equal to 0, this entire term will become 0. So I will get the value of C1 as log of Ti minus T infinity. Now let us put this value of constant C1 into equation 2. So it will give me log of T minus T infinity is equal to minus HAS over rho VCP into tau plus log of Ti minus T infinity. This is nothing but value of constant C1. After simplifying this, what I will get, this is the equation I got. Let us take log Ti minus T infinity on the left hand side. So what I will get, log of T minus T infinity minus log of Ti minus T infinity is equal to minus HAS over rho VCP into tau. From the log of logarithmic, I can write this equation as log of T minus T infinity over Ti minus T infinity is equal to minus HAS over rho VCP into tau, and T minus T infinity over Ti minus T infinity is equal to exponential of minus HAS rho VCP tau. Let's say this is equation number 3. So equation number 3 is nothing but an equation can be used to calculate the temperature of the body undergoing Newtonian heating or cooling after any interval of time tau, where T is nothing but, I can also write it as T tau as a function of time. Okay, so this equation is called as the equation of lumped parameter analysis or lumped heat capacity analysis. And from this, as you can see here, T infinity is known to me, Ti will be known to me, H will be known to me. If dimensions of the body undergoing Newtonian heating or cooling are there, are given to me, I can calculate surface area as well as volume, and density and specific heat are also known to me. And tau is the time interval at which you want to calculate this quantity. So this way you can apply this equation, find out the temperature as a function of time using lumped parameter analysis. So this is all about lumped parameter analysis. Now please remember equation number 3 is given in the heat transfer data book on page number 58. If you will refer the page number 58 of your heat transfer data book by C.P. Kothandaraman, you can find out this equation. No need to remember at all. So with this, I come to an end of this lecture. So after going through this video lecture, you will be able to explain Newtonian heating and cooling, and you will be able to explain lumped parameter analysis method to analyze transient heat conduction phenomena and to find out the variation of temperature with respect to time. So thanks for passionate listening. Happy learning.